Here's a science riddle for you. One twin leaves Earth and flies away in a spaceship at nearly the speed of light. The other twin stays on Earth. The traveling twin returns home after many years, but he or she is not the same age as the Earth-bound twin. Which twin is younger, and how much younger? Well, if you guessed that the traveling twin was younger, you're right. But you might be surprised to hear just how much younger they can be. First, let's talk about what we mean by young. In order to make things as fair as possible, let's assume both twins were born on Earth on the exact same date and time. And when they're reunited, they will both still be healthy and full of energy, which means we need to ensure neither twin experiences any significant aging effects from normal wear and tear. That rules out one way to mess with someone's age, which is to simply kill them. Killing aside, if we want to change someone's age without changing anything else about them, the only thing we can change is their location. Okay, so we have two identical twins who are the same age. They look the same, they feel the same, and they're the same height and weight. Then one decides to hop in a spaceship and blast off from Earth at half the speed of light. Now, while the twin is traveling, the other stays on Earth. This scenario is known as the twin paradox in relativity because it seems paradoxical that the twins could end up being different ages when they reunite. So let's figure out which one ends up being younger. If you've taken an introductory physics course, you probably know that time is relative. What appears to be a tick-tock of the clock is really just our best guess about how fast the universe is expanding at any given moment. Let's go back to the days of Isaac Newton, before Einstein turned our understanding of time on its head. Newton assumed that time flowed at the same rate everywhere in the universe. It seemed to make sense. If you lined up two clocks, one on Earth and one on some faraway planet, and you kept the clocks synchronized, then every second on Earth would correspond to exactly 1 second on the faraway planet. Since this was the case nearby, Newton assumed that it was also true very far away. But Einstein changed all that. He turned our conception of time on its head with his theory of special relativity. Einstein said that time must flow more slowly for objects that are moving relative to an observer. Imagine you're watching a friend approach you on a fast-moving train. As the train approaches, the ticks of their clock appear to slow down relative to your own clock. After the train passes, the ticks of their clock continue to appear slow as they recede into the distance. You might think that's weird, but it's actually correct. This is called gravitational time dilation. To understand why time dilation occurs, let's imagine our twins again, except this time let's have them closer together. The twin on Earth is stationary, and the traveling twin is moving at half the speed of light. To measure the time it takes for the traveling twin to reach a particular location, you can use the following equation. Distance equals speed times time. Solving for time gives us time equals distance over speed. Let's assume that the traveling twin wants to reach a destination that is 18 light years away. Traveling at half the speed of light, it will take 36 years for the twin to reach their destination. So according to the twin on Earth, 36 years will pass between the departure and return of their sibling. However, for the twin traveling at half the speed of light, less than 36 years will pass. For them, it takes 18 years to reach their destination, and then another 18 years to return. So, for the traveling twin, only 36 years pass between departure and return. But wait a minute, how can less time pass for the traveling twin? Time cannot pass faster on Earth than it does on the spaceship, nor can time pass more slowly on the spaceship than it does on Earth. The only explanation is that time must actually be passing more slowly for the traveling twin. Let's plug the numbers into the equation for time dilation. Time observed equals time elapsed times the square root of 1, v squared over c squared, where 5 is the velocity of the object and c is the speed of light. So time observed is equal to 36 years times the square root of 1.5 squared over the speed of light squared, which simplifies to 36 years times the square root of 3 over 2, and 36 times the square root of 3 over 2 is approximately 31.2 years. So the Earth-bound twin would observe approximately 31.2 years passing during the 36 years that the traveling twin is gone. When the traveling twin returns, they would be younger than the Earth-bound twin by 36 minus 31.2 or 4.8 years. However, this example used a lot of assumptions, like the fact that the twin traveled to a destination 18 light years away. We also assumed that the twin stayed at half the speed of light the entire time, which isn't realistic because it would take more fuel to accelerate to half the speed of light than would be reasonable for a spaceship. Plus, current technology is nowhere near the ability to even reach a significant fraction of the speed of light. Nevertheless, the twin paradox demonstrates that time is not the tick-tock on the clock we perceive it to be. Time is intertwined with space, and it's ultimately a human construct to help us keep track of changes. Now here's another fun fact about the twin paradox. Suppose the traveling twin wanted to get back to Earth as quickly as possible. In that case, they would turn around at their destination and travel at twice the speed of light towards home. According to Einstein's theory of special relativity, nothing can travel faster than the speed of light, so this presents a problem. How could the traveling twin possibly return home faster than they would if they were traveling at half the speed of light? Well, there is a solution, but it requires breaking one of the laws of physics, specifically the equivalence principle. According to the equivalence principle, gravity is just a manifestation of the curvature of spacetime. Spacetime can be curved in many ways, but the simplest example is a bowling ball on a trampoline. The ball pulls the trampoline down, and the more massive the ball, the deeper the well it creates. If you roll a marble across the trampoline, it will fall into the well created by the bowling ball. If you keep rolling the marble faster and faster, eventually it won't fall into the well because it will escape the gravitational pull of the bowling ball before getting too close. So, to avoid falling into the well, the marble must travel faster than the bowling ball. Similarly, to avoid falling into a black hole, an object must travel faster than the speed of light. To do this would require a negative mass. So, if the traveling twins somehow obtained access to negative mass, they could accelerate their ship beyond the speed of light and shorten the travel time. If the traveling twin returns home in this way, they could actually be born on Earth again before their original departure date, depending on how much negative mass they used. In other words, the traveling twin could actually become younger than their birth date. While this may sound a little crazy, it's not completely outlandish. Negative masses have never been observed, but that doesn't mean they don't exist. If they did exist, and if accessing them didn't break any other laws of physics, then traveling at superluminal speeds and even traveling backwards in time wouldn't be impossible. If you enjoyed this video, stay tuned for more. Thanks for watching.